Hi everyone, in this video, we are going to cover chapter section 8.5. After you finish watching this video, please start working on your homework as soon as possible. Okay, so in this chapter, we are going to cover how to measure heat of the reaction, or what we call enthalpy from calorimetry. Okay, so the more detail of this can be read from the OER textbook, chapter section 8.5. Okay, so calorimeter is a device that used to measure heat transfer or the heat of the reaction in this case. And in this case, we are referring as coffee cup. The reason for this is because we use the styrofoam coffee cup to prevent the exchange of the heat between the environment and the system that we are studying. Okay, so pretty much it's going to compose of, it's going to compose of the stirrer that helps mix the reaction together, and it's contained the thermometer that helps measure the temperature change before and after the reaction. And again, this reaction right here that we study is going to be within the in the insulation to prevent the exchange of the heat between the environment and the reaction. So that way we can measure the more accurate the temperature change of the reaction. Okay, so before we get to do that, I would like to talk about how the heat flow and tie that back how the temperature change as well. Okay, so the first thing that we are going to take a look at is we are going to relate the direction of the heat flow and predict how the temperature would change for both endothermic and exothermic process. Okay, so in the previous video, we're looking at the heat flow before, right? So for example, if you're looking at the difference between system and the surrounding here, because we're looking at endothermic, we know that endothermic is absorbing the system, right? We focus on the system. So the system is the one that is absorbing, this system right here is the one that absorbing heat. Therefore, in this case, the direction of the heat flow would be coming into the system, right? Because the system is absorbing heat. Therefore, if the system absorbing heat, what would you expect to be the temperature change of the thermometer then? Well, obviously it's going to drop, right? Because the heat flow from the surrounding, because the thermometer that we use is actually measuring the surrounding, right? So because the surrounding losing heat, therefore the temperature of the surrounding would drop. Therefore, you are going to see that the reading on the thermometer would decrease. Okay. Vice versa, if you talk about exothermic process, it would be the opposite, right? Because exothermic is the system release, or the reaction is releasing heat. Therefore, in this case, heat is going to be dispersed out of the system. Therefore, the surrounding would absorb that. So as it's dispersed throughout the surrounding, therefore the temperature of the surrounding would increase. Okay, so those are the two that you will need to be able to differentiate. Okay, so that way you understand better how the temperature that we measure is associated with the reaction temperature, that the reaction heat that is changing. Okay, so again, endothermic process, what you're gonna observe is that thermometer would drop, right? For exothermic would be in the opposite direction. Okay. All right, so the second one is we're going to take a look at how does the heat of the system compare to the heat of the surrounding. Okay, so in this case, I'm going to use the mathematical expression to help us to understand this, right? So because we know that if one lose, the other have to gain, and if the other one gain, the other have to lose, right? Therefore, in this case, the amount, the Q amount, or the amount of heat, they are going to be identical amount. However, they are going to have the opposite side. The side tell you whether it's going to lose or it's going to gain. So for example, in this case, it's omit that the system is plus, right? So it's gain. So that means if you are looking at system is going to be what we call exothermic, then the Q system would be negative, and then the Q surrounding would be positive, for example, right? So again, the quantity are the same, the side are the opposite, because the side tell us about how the heat flow. Okay, so the side, the only thing matter about the side is just tell us how the heat flow. Okay, all right, so I'm going to relate this to chapter 8.4 as well, that we talk about Q equal to MCAT, right? So MC delta T. So this equation right here is used to quantify the heat that is being produced or is related to the system, right? If you know a certain amount of substance, you know how the temperature change And if you know the specific heat capacity of that matter, you should be able to calculate for the heat that involved with that, right? So we learned about this in 8.4 before. Vice versa, if you are given everything else, but the mass, you can also find out mass as well, right? So that means for chapter 8.4, as I mentioned, it's going to be one unknown variable. Everything else will be given to you, right? So you just need to know how to solve those type of problem. So in this lecture, I'm going to combine those ideas. Okay, so I'm going to combine idea of 8.4 to this 8.5, which is the heat that involved with the two system, right? The surrounding and the system. Okay, so I'm going to combine them and see the heat exchange between the two objects. Okay, all right. So what we're going to focus on in this throughout this whole section is going to be the transferring heat in water. Okay, for example, if you have like a very hot pan from cooking, right? If you put that into the sink that contain water, how would that temperature affect the temperature of the temperature of the pan affect the temperature of water, right? What would be the final temperature and things like that? We're going to take a look at that, right? And also another thing that can be tied to this idea also is the transferring of heat between two objects as well. For example, if you have your partner with you right now or your children's, right, you are welcome to like hold their hands right now, right? So if you feel your hand getting warmer, it means that the heat is actually transferred from your partner to you, right? But however, if you feel the opposite, it's going to be the opposite direction, right? So that means in this case, we are looking at the same thing. So pretty much the two objects that we are going to focus on, one would be the object and the other one would be just water. So we're going to focus on this most, okay? So, but you can do that with your partner hand as well if you want to calculate how much heat involved and also what is the temperature different and things like that. You can actually use this. Okay, what I'm going to do is that I'm going to pretty much again focusing on this, but what I'm going to do is I'm going to use this idea here and we're going to combine with the 8.4 Q equal to MCAT. Okay, so Q equal to MC delta T. Okay, how do I combine that? Okay, so if you're looking at this, right, this Q is equal to this term, therefore this is also Q, this is also Q. Therefore, if I replace this Q with MC delta T, right, I can actually involve all of this with temperature, you know what I mean? So this Q right here, if I replace this with MC delta T, I can actually calculate for how the temperature change as well. Now you might be like, wait a second, but there are two different objects. Yes, there are two different objects. So that means in this case, what you're going to do is that the mass involved with this object have to be this mass, right? CS, specific heat, would be this specific heat of this, right? So same thing for water, mass have to be mass of water, specific heat has to be specific heat of water. So those two are not going to be the same because they are two different objects, okay? The initial temperature would not be the same either, because if you think about hot pan, right? So the hot pan, after it reach, after you put it in water, the initial temperature of water might not be the same as the hot pan as well. So at the end, what is going to be the same is going to be the final temperature when they reach the thermal equilibrium, right? Because if you think about it, if you hold someone's hand long enough, you will see that eventually you are not going to feel hot or cold anymore, because eventually it's going to reach that thermal equilibrium between two of you. That's when the heat stop transfer. Okay, the heat only transfer when they are different in the temperature. Okay, and it's going to transfer from a high temperature or high quantity of heat to a lower quantity of heat, which is like lower temperature. All right, so let's take a look at how to use that in an example here in a calculation problem. So we have a block of copper of an unknown mass. Okay, so we don't know mass, and it's this copper with the unknown mass has an initial temperature 85.4 degrees Celsius. Okay, so the copper is immersed in a beaker containing 195.7 grams of water at 22 degrees Celsius. Think about this. You have a hot object, you're gonna put it in cooler water. What do you think should be like, what do you think should be how the heat transfer? Well, obviously it's gonna go from a hotter object to the cooler object, right? So that means in this case, at the end, you are going to end up with a lower temperature of copper, right, and a higher temperature of water, right? So exactly what this indicates here, right? So it said that the final temperature after it's reached the thermal equilibrium is at 26.8 degrees Celsius, which makes sense because temperature of water should rise, right? And then temperature of copper should drop, right? Because heat transfer from a higher to lower. Okay, clear? Okay, so next thing, what should we do here is that we are looking at how the object transfer to heat to water. So that means we're gonna use heat of the copper because copper contains heat, right? Because it has at a high temperature here, and it's gonna equal to the amount of heat that water receive. Remember, it's not going to be more or less because the same amount that lose is have to be gained by something else. So therefore, in this case, Q of copper, heat of copper have to be the same, identical to the amount of heat that water receive. The only thing that is going to be different would be what? The sign, right? So in this case, which one is losing heat? Well, we know that copper is losing heat. So therefore, I'm going to add the negative in front of Q of the copper. Okay. All right, next. Well, as I mentioned before, these are the given information. The next thing that we need to know is that, well, we know that we want to know the mass, right? So that's what we don't know. Okay, so what I'm gonna do is I'm gonna tie this Q right here as I mentioned before, that from chapter 8.4, we know that Q equal to MC delta T. Therefore, all I have to do is just, I'm gonna replace all this Q with the MC delta T. So I did that, right? So this is belong to copper. So that's therefore all of these are going to be belong to copper. Okay, same thing, because this side of equation is belong to water. Therefore, you have to make sure that all of this mass, specific heat, and delta T have to be belong to water. Okay, so you have to do that correctly. All right, next thing, what we're gonna do is we are going to have to look at the specific heat capacity of copper and water, so that way we can solve for this, because that is what do you call a constant value. Okay, so if it's asking you for it, it will tell you on the problem, but in this case, you just have to look it up. On the exam, this table would be provided for you. Okay, so you just need to use it on the exam. I will have a table provided for you. Okay, so if I do this, I'm going to first help rearrange the equation first, so that way it's just less messy for me. So because I want to know mass of copper, so I'm going to get rid of this term first by dividing it. Okay, so because we have a negative side here too, so I'm gonna divide by negative of that term, both sides. Okay, so if I do that, I'm going to get rid of this term, right? So pretty much I'm gonna get rid of this term right here. Okay, so therefore I will have only mass of copper. Okay, so then you are going to replace all of this term what we know. Okay, so you're going to replace with mass of water, specific heat of water, right? And then change of temperature, that's what we're going to take a look at. Okay, so that's mass of water, specific heat of water. And remember, change have to always final minus initial. So in this case, we're looking at final temperature. Final temperature is when it's reached the equilibrium, right, which is 26.8. For water, this is the delta T of water. The initial temperature of water is 20.2. So therefore, you're just gonna subtract that, right? And then divide by the specific heat of copper. Don't forget the negative side, okay? And again, because of copper, final is 26 degrees, so sorry, 26.8 degrees Celsius, but the initial temperature of copper is at 85.4. So you need to do final minus initial, okay? So that's how you're gonna get delta T. Okay, if you do math correctly, your mass of copper would come out to be 240 grams of copper. And again, we are dealing with 4 significant figures. So, sorry, 3 sig fig. So where's 3 sig fig coming from? Well, it's gonna come from, you know, like at this one right here. Okay, actually the given information is contained 3 sig fig. So therefore, in this case, you are going to get 3 sig fig for the final answer. All right, so number 4, you are going to, for number 4, it's going to be similar to the previous one, but asking you to find different quantity. I would like you to pause a video for a second right now. Okay, complete this problem yourself, so that way you can check your understanding right away. And after you finish, then resume the video again. Okay, so do not look at the solution yet. Okay, so pause the video for now, complete it, and resume the video after you finish. All right, let's take a look at your answer together. Okay, so in this case, it's giving you aluminum a certain amount, right? And also it's giving you the initial temperature that's submerged in water at a certain temperature and asking you to find out the final temperature. Okay, so in this case, same thing again. We know that we're looking at object transferring heat. So in this case, you are going to have a negative sign in the aluminum again, because aluminum has a higher temperature than what water is. Think about this. Remember, aluminum has higher temperature at 79, right? And then it's submerged into water, which is at 21.8 degrees Celsius. You should therefore expect that the final temperature should be lower than 79.4, right? Because it have to be lower than that, right? And it should be higher than 21.8, right? So this would be the range of final temperature. It should be within that range. Why? Well, because temperature of aluminum have to drop, right? And temperature of water have to increase, therefore it's going to be within that range. If your answer come out not within this range, you are doing something wrong. Okay, so that's how we check our answer here. Okay, so let's take a look at this. So I'm going to do the same thing. I'm going to extract all those given information. Okay, so what we are looking at is the final temperature. Okay, so what I'm going to do the same thing, right? So I'm going to start with replacing those Q with the MC delta T for each of those substances. Okay, so again, we are looking at water, so that's why we are looking at aluminum and water. You can do that with something else too. So if I say that if you have two objects, aluminum touches with copper cube, right? You can do that too. And instead of having water, you can just change it to copper, right? So this part right here is applied to everything. Okay, so it's applied for the transferring heat between two objects. This can be between your hand and your partner hand as well. Okay. All right, so I'm gonna go ahead. So in this case, I'm gonna go ahead, look it up, the value for the specific heat for aluminum and also water. Okay, so I need more space, so I'm gonna shrink off this. Okay, so let's bear with me here. So I'm gonna add all of this mass and specific heat together. Okay, so with delta T, tell me again, what do you use? My final minus initial or initial minus final, sorry. The answer is in finals, right? Minus initial. So in this case, because we don't know final, therefore I'm just gonna leave it as TF. Okay. Do the same thing for water. We use mass of water, specific heat of water, and then we do T final minus initial temperature of water. So remember, these final temperature should be the same. Therefore, these two are considered to be just one unknown variable. It's just one variable, right? Because these two are the same, because eventually both objects have to reach to the same temperature, right? So that means this TF would be the same identical value. So that means in this case, we have only one unknown variable. So you should be able to solve it for it. Okay, so what I would do is first, I just, in this step right here, I just multiply these two, right, to get that value. Okay, so the next part, I'm doing the same thing. I multiply this to get this value right here. Okay, the next thing is I'm going to start to distribute to the parentheses. Okay, so distribute this value into the parentheses, right? Because multiplication, you just multiply throughout that whole parentheses. You do the same thing for the other side. Okay. Next, we are going to make sure that the unknown variable are on the same side. So what I'm gonna do is I'm gonna move the number to be together first. So this number right here, I'm going to move to this side, right, by subtract this number on both sides. Okay. So what you're gonna get is this number going to cancel each other out. So that's why it's empty right there. And this come out to be this much. Okay. The next thing we're gonna do is we are going to make sure that the unknown variable are on the same side. So I'm gonna move this whole thing to the other side. Okay. So in order to do that, we are going to subtract both sides with the same unknown variable. Okay. And you are going to get this. Okay, so the next thing, the final step would be what, divide both sides by the number in front of unknown variable, right? So your final temperature come out to be 22.9 degrees Celsius. Well, makes sense, right? Because it's between 79.4 and 21.8, so it's been in between that. You might ask, how come that this temperature is closer to water but it's so much away from the initial temperature of aluminum. Remember in chapter 8 point, I believe 8.3, we talk about specific heat capacity before. Obviously we see that specific heat capacity of water is so much, right? Is higher than what do you call it, than aluminum. So water can hold more heat than aluminum without much of changing in the temperature. So that's why you see that the temperature of water doesn't change much at all in comparison to the aluminum, because water has higher specific heat capacity, okay, as we discussed in chapter 8.3. All right, so again, so this is what I just mentioned. Okay, so if you want to jot that note, that's the note for it. All right, so the next thing, so again, so this is the note right here. You can jot this down, okay? Right, so if you want to jot it down, pause the video and jot it. So I'm just gonna go to the next slide now. Okay, so the next thing we're gonna take a look at is we are going to take a look at the reaction in the solution. The previous one, you have two objects that doesn't dissolve in each other. For example, if you add aluminum into water, it doesn't dissolve it into water, right? Aluminum still stay as that chunk of aluminum. But in this case, we're gonna take a look at some chemicals that you add to water, then it will disappear or it will dissolve, what it said, like is dissolved and become aqueous solution. So in this case, for example, salt, right? If you add salt into the solution, eventually it's going to disperse throughout the solution, it's dissolved, right? You no longer see that crystal salt anymore, right? So how we are going to measure that? So that's what we're going to take a look at. And this is what the coffee cup calorimeter actually will be used for. You are going to do more of this study when we are looking at the lab. I think one of the lab, I think later on when we're looking at hot pack and cold pack. Okay, so you are going to make your own hot pack and cold pack, and that's what you are going to take a look at this coffee cup calorimetry again. Okay, so again, so in this case, what we're going to look at is we are going to take a look at how the temperature of the solution change, right? So remember I mentioned before, like this coffee cup right here, in order to measure the heat of the system, you are going to have to rely on the surrounding, right? How we measure the surrounding, right? So for example, if the system is expelling heat, this thermometer right here is going to increase its temperature, right? So therefore, in this case, what we are looking at is we are going to quantify heat of the reaction, because we want to know if you dissolve this salt into this water, how much heat would involve with that. Okay. However, when we are measuring the temperature change, we are measuring temperature change of the solution, which is we're relying on the surrounding. Okay, so this is more like a surrounding. Okay, so therefore in this case, this is surrounding. Okay, therefore the sign would be the opposite, because similar to what we mentioned earlier, which is Q reaction, right? Or Q system is equal to Q of the surrounding. Okay, so it's similar to that, but with the opposite side. So this is what it is for. Okay, so same thing here, but the thing that is going to increase a little bit more is the term solution. You need to understand what is solution. Okay, solution is the aqueous solution that we are going to use is the combination between water and the chemical that you use. For example, in this case, the solution would be the salt and together with water, that is considered to be solution. Okay, so that means when you are using this equation right here, you need to make sure that everything belongs to the solution. Again, the solution is not just the chemical, it's not just water, it is both water and the chemicals. Okay, so in this case, the mass have to be mass of water and chemicals. The specific heat would be of that particular solution that combine of those two together. Okay. Again, because heat of reaction is the enthalpy change, right? So therefore, in this case, you can also use the delta H subscript reaction as well, which is referred as enthalpy change of the reaction or heat change of the reaction. Okay. Oops, sorry. This equation right here would be given on the exam. Okay, so you just need to know how to use it. Okay, so let me take a look at. Let me walk you through the example so that way you understand it better. So an example of coffee cup calorimetry problem would contain the word solution or something like dissolve in something else, and it will involve with heat. Okay, so in this case, we are going to react hydrochloric acid with silver nitrate. Okay, so this is going to precipitate or form a solid product, which is called, in this case, it produced silver chloride, and another product would be nitric acid. Okay, so it tells you that this reaction right here, when 50 milliliter of 1 molar silver nitrate, okay, combined with 50 milliliter of 1 molar hydrochloric acid, okay, in a coffee cup calorimeter, the temperature changed from this to this, right? So it seemed like temperature increased, right? 21 to 23.4, that's increased. Now tell me, is that exothermic or endothermic? If temperature increased, yeah, it seems like this reaction is exothermic, right? It's asking you to calculate delta H, so that means you should expect that your delta H should come out to be a positive value, right? Sorry, a negative value, because this is exothermic, right? So we should expect delta H to be a negative, okay? So for this reaction, written blah blah, right? And it's giving you the density, and also give you specific heat of water. Okay. All right. So what should we do here? Okay. So first off, erase all that. Okay. So the keyword of this again, the keyword for this type of problem would be given, would be like coffee cup, the word solution. That's when you know that you are going to use the this equation right here, right? This is involved with the coffee cup equation, which is of the solution. So instead of using water, you're just going to use the word solution in this case, okay? And instead of object, it's going to be of the reaction. Okay, so mass of the solution. Okay, so how do we know the mass of the solution now? Well, the mass of the solution here, if you're looking at this, some of you might not know what is this unit mean. You're going to learn that later in chapter 11 when we talk about concentration. Right now, it doesn't matter. You don't have to know it. It just tells you about concentration. But what we can use is we can use the volume that is given, right? So the volume that is given right now is giving you 50 milliliter of both, right, of these two. Okay, so it's giving you both volume of the two substance that you're gonna combine. Therefore, that means the solution would be the overall, that combination of those two. Therefore, all I have to do is I just need to add those two volume together, right, to get a total volume or the volume of the solution. Okay. Now, how do I go from volume to mass? Well, it's given you density, right? This is the density of the solution. Therefore, in this case, you can use that, right? So you can convert this volume of the solution to the density of the solution, which is given as 1 gram per milliliter. Note that the density is not always going to be 1 grams per 1 milliliter. It depends on how concentrated those are. Some of the solution that are very concentrated is going to be thicker, therefore the density would be higher, right? So you just need to use what is given. So in this case, given 1, so you just use 1. Okay, so now we know mass of the solution. We know this term now. Okay, the next thing is we are going to need to look at the specific heat of the solution. Well, obviously it's giving you specific heat, one value right here. Okay, so that means in this case, that is going to be the specific heat of the solution is given. Do we know delta T? Well, obviously it's giving you both temperatures, so we should, right? So that means in this case, all you need to do is plug those in. Remember, temperature is final minus initial. Okay, so don't forget that, because if you forget that, then your sign of your final answer would come out incorrectly. If you do this, your delta H come out to be a negative value, exactly what we expect, right? Because this is an exothermic reaction. Okay, so it's releasing heat, so it should come out to be a negative value, 3 sig figs. So therefore, your answer would have 3 sig figs. Okay. All right. So now it's your turn now. Okay. So I'm going to let you read this problem and complete it yourself, and resume the video again when you're ready. All right, let's check your answer together. Okay, so in this case, we are looking at an instant cold pack reaction of dissolving of the ammonium nitrate in water. So solid ammonium then become ammonium aqueous and nitrate aqueous. Okay, so in this case, it's telling you that the temperature of the enthalpy, it's asking you to measure the enthalpy change, which is the heat of reaction and change, which is the delta H, right? So this is enthalpy. Okay, so we need to find this, right? Because asking us to calculate the change in enthalpy. Oh, and it's asking in kilojoule. Okay, so don't forget that. Okay, so what is the keyword here? Okay, so again, the keyword here is the word solution. Okay, so we have the word solution here. It's talk about heat as well. So the word heat, the word dissolve in solution. So those are what we're gonna use is gonna be this equation right here. Okay, so again, so this one, do we know mass of the solution? Well, let's read it. We know that 1.25 grams of NH4NO3 ammonium nitrate, okay, dissolved in enough water to make 250 milliliter of solution. Oh, hey, actually we know the volume of the solution, right? Because this is the volume of the solution. Okay, this value here, 125 is only of ammonium nitrate. Remember when you dissolve something, right, you have water here, right? And then when you dissolve NH4NO3 ammonium nitrate together, right? Together, this plus these two, right? These two plus add together, that would be the solution. And therefore, in this case, this is only the mass of ammonium nitrate, it's not mass of water. So we cannot use that. So in this case, I'm going to use the volume of the solution. Okay, so because volume of solution given, therefore we know that the density probably going to be given as well. Yep, and it's given to us. It's 1 gram to 1 milliliter. Again, the density might change with other problem. Okay, so don't stick with just 1 grams per 1 milliliter. Okay. All right, now after we know mass of the solution, because we're looking at the solution, then all you need to do is just use mass of solution multiplied by specific heat that is given, and then multiply by the temperature. Think about this temperature that you are looking at is decreasing, right? It's going from 26, about 26 to 22. So it's decreasing. Therefore, in this case, the system is absorbing heat from the surrounding. That's why the temperature dropped. Therefore, in this case, we should expect your delta H to come out to be a positive value because this reaction should be a positive, like an endothermic, right? Positive endothermic. Okay, so it's come out to be 408 joule. But remember, it's asking for kilojoule, so you need to actually do one conversion to convert that to kilojoule, right? So this conversion would be 1,000 joule is in 1 kilojoule. Okay, so that would be your final answer. And again, this reaction absorbs heat because temperature go from a higher temperature to lower temperature, indicate that this reaction is absorbing heat from the surrounding. Okay, so when you are working on your problem, when you finish and get the final answer, make sure that you think about what you are doing and make sure that it makes sense with what you are given with those given information. Okay, so if it doesn't make sense, it just means that there might be a step that you missed. Okay, all right, the summary of this lecture would be we're looking at object transferring heat, right? We're looking at water and object, hot object transfer. We use the Q equal to MCAT from 8.4 to help us determine the temperature change and how the heat transfer between those two objects. And we also look at the heat of the reaction when we dissolve salt into water to make an aqueous solution, right? So we're looking at the heat involved in the process of making solution. Okay, so the homework that associated with this would be the paper homework. Again, the reason why I have to assign paper homework because some of the problem in Newton homework is too challenging and it's not appropriate for your level. So I just that's why I have to like just not assign those and just assign the one that is similar to the lecture manual instead. Okay, so this problem right here, 1 to 3 would be more practice for this chapter. Okay, so please make sure that you complete this homework, okay, and then submit it on Moodle. Okay, so that would help you to learn a lot. All right, so if you're looking at, so the hint for this, if you're looking at 1, right? So if you're looking at 1, it would be the transfer heat between object and water, right? Because it's talking about hot object, iron skillet, right? And it's talk about like the keyword is water right here. So that's how I know is the transferring heat between two objects. The second one is talk about, oh, dissolve in water. Ooh, remember when you see the word dissolve, you are making solution, right? So this is going to be the heat of the reaction that involved with the solution. So you're going to use this equation instead. The last one, what is it? Okay, so the last one, what we are looking at is you are looking at heat is actually already given heat. Okay, so this is, you might have to think about what is given, what is asking. Okay, so that should be only one unknown variable. Okay, so that means this case is already giving you Q, but it's in kilojoule. Okay, so you have to think about that. Now it's asking you to find out what final temperature, right? How would your body temperature become, right? So it is actually asking for final temperature. So that means in this case, you are going to find out TF instead. Okay. One thing I want to point out for this is that this, if you're looking at this, right, you should use the solution Q. Why do you use solution? Well, because this one we talk about the water inside the body. Okay, so that means is body and water together. So that could be like have like a solution, right? So in this case, you're gonna use this Qx equal to M solution, C solution, delta T solution. Okay. All right. Again, if you have any question, do not hesitate to reach out to me. Okay, so start your homework at 8.5 right away. Thank you for watching.